Okay, question 5. Student's got a bar magnet. Oh, let's pick a coloured pen. Yeah, student has a bar magnet, a piece of iron, the same size as the magnet, and some paper clips. Describe how the student could use these to demonstrate temporary induced magnetism. So what this is not asking you to do, like when I got you to make a compass, is get your bar magnet, stroke it, because that's how we induce permanent magnetism. So because it's put this piece of iron in there, that's going to trick some students. This is not saying how do I align all the magnetic fields, it's how do I form temporary magnetism. Well, the basic idea is if I've got a bar magnet north-south, if I hang a paper clip on there, that'll be south-north. If I hang another one on there, that'll be south-north. And that'll be temporary. That'll only be there. If I take that magnet away, these will then all fall to the ground. That's the basic idea. Temporary magnetism is one that's induced when the magnet is on you or near you. And as soon as I take the permanent magnet away, you're no longer magnetic. Okay. So model answer, pick up one paper clip with a magnet. So I'm going to sketch a little picture here. Here's what I'm saying. Whoops. Get my bar magnet, get a dodgy bar magnet, pick up one paper clip. And we know that that'll do that. And it'll be fine for you to draw this in the exam as well. Well, the next thing is, see if I can pick up another bar magnet. So see if the second paper magnet is attracted to the first. And I'm now going to say, so I'd end up with that. Okay, next part. So I've now proven that this is temporary magnetism because this has become magnetic because it's now attracting that. Perfect. So, but this is basic idea. I'm going to need to have at least 2 paper clips to prove it. Well, the next part is now I've got to show it's temporary. And to show it's temporary, it's take this away. Take the bar magnet away. So the second part, remove the magnet from the first paper clip. The second should fall off because that magnetism was temporary. It was only there when the permanent magnet was near it. Okay. Next question. Student sets up the apparatus shown in figure 9. And it says when the current in the solenoid is on, so we've got this is going to be connected to power supply and current's going to be going, say, up and out. I could equally put those arrows the other way around because we don't know which way it goes, but it doesn't matter. So describe how the student could use the apparatus to investigate how the size of the current, so that's I, so we're going to change you, so we're going to have to talk about that, affects the force of attraction between the solenoid and the iron nail. So what this is saying is when I pass current through that, we're going to make a magnetic field. This magnetic field is going to attract the iron downwards. Because it's going to attract this downwards, it's going to pull on this spring. Now the next part is, and we're using a little marker here to measure how much the spring extends. So what have we got? Well, we've got Hooke's law here. So this is a complicated question because we've got this idea of induced magnetism, current going in, that making an attraction, that pulling on a spring. And we've got Hooke's law here. So that's Kentucky Fried X-rays that I taught you last year. Okay, so that's all of those basic ideas. I'm going to get rid of this confusing bit, but now we've got this basic idea that we're going to need Hooke's law to explain what's going on. So the basic idea then is we're going to change this. So I'm going to put a little 1 there. I'm going to have some idea of me increasing the current. Then we're going to have some idea that I'm going to measure the length at the start, then measure the length of the end, and that's going to be the attraction. But that's the extension, so that's X part of Hooke's law. We want to work out the force. So we are going to need to know the spring constant. And I'm going to have to just say that in my question. Well, I'm going to assume that we know the value K for the spring. And here's your model answer. So note the pointer with no current. So that's the start. So if I just change my colour on this, that's this bit. Next part. Use an ammeter to measure the current, and we're going to set it to 0, 1, 2, 3, 4, 5, 6. That's this bit. So 1, 2, 3, 4, 5, 6. We're going to change you. So that's the independent. And what we're going to do, we're going to measure the extension. So that's going to be coming next. Measure the extension of the spring after each one of those current values. And then the tricky part, we want the force. So we can see here, F equals Kx. So the last part is a mark that the examiner's report said was mostly missed. So we then use the formula force equals the spring constant times the extension to calculate the force. Done. Tricky question. So now we've got a question on this because we've got spring constant. Let's just change my colour. And you're pretty good at this last year. So the spring constant, so this is K, and I'll just get that ready. Kentucky Fried X-rays. We can see that's in newtons per metre. The string, the extensions, that's X, 12 centimetres. So I'm changing you to 0.12 metres. They need to speak to each other. Calculate the energy transferred by extending the spring. So now that we've done that unit change to get you into metres, we're away. So the elastic potential energy is half kx squared. If you didn't know it, it didn't matter. It will be in your equation list at the back. So now I'm going to go, well, 0.5 times the spring constant K, 24, multiplied by the extension squared, 0.12 squared. And that gives me that 0.173 joules. Done.